scenario, we are to start off completing the table of differences, and it appears we're also to complete the y ratios. Why would we be doing this? Well, it's because of the first bullet point. We want to answer the question, can this data be modeled by a linear function, y or y not? So, what are the key things that we know? Well, we know that linear is going to have a constant rate of change. So, let's see if I can get my pen here. So, we are looking for a constant rate of change because linear has constant change. That is the key characteristic. So change in y, we know is the formula y2 minus y1. And so looking at our data, we're told up here at the top that there is the number of data, a number of bacteria after an antibiotic is introduced. We are to use X for the hours since the antibiotic has been added to the Petri dish and Y for the number of bacteria. So from 0 to 1, to figure out the change, I would take the 1500, which is my Y2 value, and I would subtract the 3000. And when I do that, I do get a negative because the number of bacteria has decreased because the antibiotic is killing them off, and I get negative 1500. I'm going to repeat this process the whole way across. So from 1 to 2, my Y2 is 750. Subtract out 1500. And when I do that math, I get negative 750 as my answer. And so already these two do not match. And down here, can this be modeled by a linear function? No. But I am going to finish my chart. So I'll subtract 375 minus 750, and that gives me a negative 375. And I'll take 188 minus 375, and that gives me a negative 187. So going down here, can it be modeled by a linear function? No, absolutely not. Why not? The change is not constant. Last week then, we talked about the second most common function, which is exponential. And we talked about in exponential data, if you have a constant y ratio, then you could use an exponential function. So I have us going through and looking at our y ratios. Our y ratios are always the y2 value divided by the y1. So in this case, my y2 is 1500 divided by y1 of 3000. And that comes out to 0.5. And then from data hours 1 to 2, so our second grouping of data here, we would have 750 over 1500, which is also 0.5. We would then have 375 divided by 750, which is also 0.5. And then our final one does not come out exact because of rounding. So we'd have 188 divided by 375. And let me write that out here, 188 divided by 375. When I type that on my calculator, I get 0.501, etc. And so even if I'd round to 2 decimals, though, it would be 0.5. And that's just because we would anticipate bacteria being whole numbers. So, looking at the questions here. Question 1 we answered, the change is not constant, so it's not linear. Since it's not linear, we cannot do bullet point 2, we cannot find a linear model. Question 3, could this be an exponential function? The answer is yes. And the reason why is the y ratios are constant. And then although this is not the focus of the lessons this week, we did talk about it last week, and so as way of review, when we're working with data, we have an NPAT formula. In the NPAT formula, the P is the start, and the A is the ratio, and the T variable is our time. So I can very easily write an NPAT formula for this because of that constant ratio. So at time of 0, this Petri dish started with 3,000 of the bacteria. And then we have our common ratio of 0.5 exponent of T. So they were multiplied by 1/2 every single hour to get the new value.